We'll get started here at day 2 of Intro to Unix. Hopefully we're all semi-awake. And we'll kind of run through stuff like we did yesterday. I'll try to, give us a 5 or 6 minute break kind of every hour or so we can kind of get up and get more coffee or stretch or do whatever we need to do. And we should hopefully get going. So hopefully yesterday we all feel pretty comfortable, at least with the general setup of the Unix system, and we learned things like how to find out where we are in a system, how to change directories, how to list the directory contents, and a bunch of stuff about how to copy, move, or remove files and directories on our system. So today we're going to get started. We'll log on to Hoffman again. Let's see. Yep. All right. And log into Hoffman like we did before. Hopefully now we are sort of comfortable with that. So we'll open up whatever we're using for our shell. I'm going to make it larger so we can read it. Computer's maybe not happy. All right, there we are. Sorry, I don't know why that's wanting to be slow right now. I'm just changing our text size so if we can read it. We're following along. And remember, we log into Hoffman using the SSH command. So we're asking for a secure shell. And it's, my name or whatever your username is at hoffman2.idre.ucla.edu. And we should get prompted to ask for a password. And remember, while we type our password, nothing's going to show up for security. And then we kind of our little login message. And hopefully we're happy and we've logged in. I'm going to give us just a second to make sure. All right, make sure we're there. And then the next thing we're going to do is we're going to request an interactive shell. And what this is going to do is change everything we're doing on Hoffman from happening on the login node to on one of the computational nodes. And this is always kind of good practice. Yesterday, everything we were doing when we were making directories and that sort of stuff is completely fine to do on the login nodes. You can edit text files and things like that. But when you start performing kind of computational tasks, it's better to move away from the login node and be somewhere where we can, we're not affecting other people's ability to do things on Hoffman, and we're kind of in the appropriate place where we should be for performing tasks that are going to maybe use a little bit of memory or time. And so the command to get an interactive shell is qrsh. And then we're going to request some resources using the flag L command. And then we're going to request here 3 hours and 2 gigs of data. And this request for data and time, there can be no spaces or anything in it after the commas or that sort of thing. So I'm going to ask for 3 hours and 2 gigs of RAM. And that's way more RAM than we're going to need today, but just it's fine to be safe. And what this is going to do is it might take a moment, and we can see right here, I'm currently on login node 4, and this is going to move me on Hoffman from login node 4 to one of the computational nodes. And I know right now we have maybe 40 people all requesting this at once, and so it might take a moment. And what this is going to do is it's going to bring us to one of those computational nodes on Hoffman, which is nice. And when we're requesting 3 hours and 2 gigs of RAM, it won't grant us that position on Hoffman until it kind of has allocated that for us and reserve that data and that much time for us. And maybe, like I said, as 40 people are doing this all at once, it's going to take a moment. But what we'll see is my position change from login 4 to one of the computational nodes. And I think for that question, yeah, so the QRSH is a Hoffman specific command. And so now, yeah, so that was a good question that someone was asking. And so you're going to find if you work on different high performance computing clusters, different systems use different queues for allocating resources. There are some queue programs. Some people use something called Slurm. Some people, no, there's a couple other ones. I can't remember what all they're called, but there's a handful of these different systems that people use, and they use them to request resources in the queue on these systems. And you kind of have to get to learn the syntax of your specific system you're working on when you're requesting these resources. Let's make sure. All right. Oh yeah, good point. You can also make a program with the interactive shell. And so we're going to kind of talk more about shells and stuff. One thing we're going to notice is if I go up now, I'm actually not going to have commands or the commands that I was using previously because I'm somewhere else on Hoffman. I'm going to have the commands I typed last time I was in interactive shell. But if we wanted to save this, we could do it in a couple ways. We could nano and write QRSH, flag L, and then the resources we want, and save it into a text file that we could run later. Or we could echo that as well if we wanted to go up. I'm not going to exit out because it took a minute to give me that resources, but I'll show us here. And we'll talk more about exactly what all we're doing here kind of throughout the next day or so. But I can echo this, and I'm not going to run it now. I'm going to redirect that echo into, I'm going to call it interactive 2 because I already have one, .shell. And so if we less interactive 2.shell, that command is now in there. And so we can turn this interactive.shell into a script that we can run. And I'll show us more about how we can do that later if we want. But it's kind of nice, a nice way to remember these commands and not have to type them every time. Are we all hopefully with me? Wait. So folks are having a little bit of trouble there. It looks like. So people are saying the command in the PDF didn't have, if you're trying to copy commands out of the PDF, they're not gonna work for you. So I'm gonna give us a moment to let us catch up here. But if you like literally, come here into the PDF or I guess I don't have the PowerPoint for you. Try to copy this and then run it. The syntax for how things are recorded in the PDF won't work. You actually have to type it. Are folks that are all getting caught or having trouble, are they actually typing this command? I'll leave it up for a second. Yeah, no, this whole request for resources, the time and data can't have any spaces anywhere in it. If you put a space in it, it is going to expect something else from you. Hopefully we're getting there. All right, so we're gonna move on. Hopefully we're not gonna go too quick here. The next thing we're gonna do is we're gonna get some of the resources for the next couple days. And what I've done is I've hosted these resources on GitHub, and GitHub is a repository for code. You don't want to use GitHub to store files or things you care about or that sort of thing. But you can, it's generally a place where people share kind of code for different things, and all sorts of programs, for example, get hosted on GitHub. And you can use GitHub in a number of different ways. One is you can go to the GitHub site for a specific program or a specific person and download something and upload it, or you can clone it directly to your computer, and you can clone it to your Hoffman cluster. And so what we're going to do, and this again, I'm sorry, it's going to be a little, you have to type it perfectly, but the command, oh, and maybe we'll move somewhere. So I'm just going to move into test where I was yesterday. You don't need to do that if you don't want to, but we're going to pull resources and data for the next couple days of the workshop. And the command there is git clone. And then we're going to tell it what we want to clone. So we're cloning from github.com. Here I am on GitHub. I'm pscott17. And then we're going to clone everything in a folder called Intro to Unix. .git. And so we're going to pull then stuff from GitHub, where I've hosted a bunch of files, now to our Hoffman account. Are we all hopefully okay? Just gonna. So someone was also asking about how, this is maybe a good point as well, about when you're getting an interactive shell, how much data do you know to request? Unfortunately, that's something that you have to learn through experience. And so, you know, I'll show us actually when we're running scripts tomorrow, how to check how much memory something used. And so that's something you often want to do, is test out how well something works. And then once you kind of figure out the resources you need, you can kind of request the appropriate amount of resources for something. And unfortunately, you can't kind of figure that out ahead of time. It's an experience issue. And so if we've done this, if we type ls, hopefully now we see this directory Intro to Unix. And if we cd into it and type ls, we got a bunch of stuff in here. I'm gonna make it bigger. We have some shell scripts, which I wrote. Here's actually last quarter's PDFs. We have a bunch of text files, which we're going to manipulate. And we have some FASTQ data and a reference genome that we're going to work with tomorrow when we're learning how to run scripts and that sort of thing. Ooh, shoot. Sorry. All right, I'm just gonna make sure. So let's see. I'm gonna, hopefully folks are getting stuff to work. If you want to see that git clone command again, it should work. It's this git clone, git tell it the whole address, and you'll get you get some information when you run it. You know, it tells you it's initializing an empty Git repository, and then it tells you that it's grabbing these objects. And so that's all standard. That's okay. And so, like I said, you know, if we go into that directory and we type ls, we can see we got a bunch of stuff in there. And this is all stuff that we're going to be working with over the next few days. So before we kind of get into some data manipulation, I wanted to talk a little bit more about relative versus absolute path, because when you're performing an action on something, you need to specify the path to where what you want to work on is. And so, you know, you can kind of have a relative path, which is, you know, the object you want to work on, you know, my favorite file. But the absolute path for that is my favorite file is hosted on u home p scott17 test new my favorite file, etc. And so you need to be able to specify the path to what you want to act on from where you are in the computer. And so if I'm in, you know, test new, let me go. If I'm in new and I wanted to work on large text, which is back a directory, you know, I can either type, you know, less, and now I'm specifying I want a less, so I want to see what's in large text, but I know large text is back one directory, and then there's large text, and that's going to be a kind of relative path, and then I can see what's in that file. I could also give it the absolute path. Which is that u home p scott17 test large text. And I'll get the same thing. And so you just need to be able to specify when you're working on something, the path to where you're working on. If that works. Are folks still? All right. Looks like folks are handling themselves. Great. And so the other thing that's important about files is file permissions. And so every file in Unix has associated permissions, and these allow you to understand what you can do to something. And so this is important because it allows users to prevent others from, you know, reading or writing or executing their files. So for example, why can't I go into your directory on Hoffman and change your files? Why can't I take your favorite FASTQ data and manipulate them, etc. And then it also, you want to be careful about what you can execute. And so for example, you know, if I, you know, download a script I'm not sure about, I don't want it to, you know, start running and, you know, creating viruses or whatever on my computer. And so the file permissions also allow, if you can run what's in, allow you to set if you're allowed to run what's inside a script. And so how do we find the file permissions is we use the ls flag L command for long. And then we can specify a file name if we wanted to. So I could use ls flag L. I'm going to actually go back one directory. Ls flag L, large text. And we have a bunch of information. About the file. We can see there's large.txt. We can see when it was last manipulated. We can see how large it is. We can see information about who owns it. And so I own it. Here, PScott17. And we see information about our group. So I'm part of my PI's lab group here. And then we have this information up here. And this is information about what we can do to that file. And read means you can read only. Write means you can write it. And X means you can execute it. And that grants permission to perform an action on that's contained within a file itself. And there's kind of three types of people in the world that can read, write, or execute a file. And these people are U, and U is going to be the second through fourth set of spaces. There's the group, and so that's other people in my group, and that's going to be the next three spaces. And then lastly, there's the world, and so this means anyone else can do something to a file. And so here we can see I can read and write, but I can't execute large text. People in my group can read it, and the world can actually read it, which means anyone that has access to Hoffman and can get on my in my directory can read this. Although I think Hoffman's set up in a way that other people don't have permission to enter my directory, so it's kind of okay. And we can see some things maybe are a directory, and if they're a directory, then we'll get a D in this first spot. So if I type LH here, we can see Intro to Unix is a directory, new is a directory, new dir is a directory. You know, this is now considered a file because it's zipped. Large text is a file, and some of these directories, at least, you know, I can execute, people in my group can execute, and the world can execute. At least how we have them set now. And so the command chmod stands for change mode, and this is how you can change the file permissions on something. And so the general syntax here is chmod, and then you can say user, group, others, or all. So U, G, O, or A. You can add a plus or a minus, and then the permission you want to have that file. And so if we want to make something, for example, readable or writable, or take away a file permission, you can do that using chmod. So if we wanted to practice that, so for example, if I wanted to add the ability to run large text, I could do that if I thought there's a scripter there I wanted to run. So it's chmod, and I'm going to do U plus X, large text. Maybe type LS, LH again. Now we can see the permission here has changed. I've added the executability to this. And in my, at least, situation of Cygwin, the color here has changed. And so if something executable is green, I'll have my computer set up. And probably if you have Cygwin, that's the same case as well. If I wanted to take that permission away, I would do U minus X, large text. And if I type LS, LH again, now we can see that permission is taken away. I could also do things like prevent other people from reading it. So I can do chmod O minus R, large text. And we can see now other people have have lost the ability to read what's in large text. And so maybe we've seen something, remember yesterday we were talking about ways that you can do things, for example, creating a tarred directory that's zipped to prevent or preserve your data. The other thing you can do is you can actually take away temporarily your permission to, for example, write large text. So I could do chmod A minus write large text. Now I only have the permission to read it. And so I can kind of prevent myself from, you know, modifying the content of that file if I cared about it. And so hopefully that's nice. Oh. So that's hopefully useful. And so we've done this a little bit before, or we've at least seen it happen, is redirection. And so that is going to, I need to plug in my computer real fast. Redirection is going to change then what happens to the output of what we're doing. And so the standard behavior of running a program is to display that program's output into the terminal. So if you remember maybe a few minutes ago, I was saying we could like echo something and then we redirected it. There we are. If I didn't redirect that echo and I hit enter, the behavior of echo, the program echo, is to repeat what you're telling it in quotes. And so I said echo, you know, QRSH, you know, the script to create an interactive shell, and I hit enter, and what does it do? It just spits it back out to the screen. So that's the standard behavior of any program, is to display the output into terminal. We can use a redirect to then, as opposed to setting it to the standard output, this will take the output of this program and pipe that output to whatever file we're redirecting it to. And that's what we did with when I did this. So now the output of echo is going to be saved in interactive2.shell. We want to be careful with these redirects because they overwrite any existing data in a file. And so, you know, I think we saw that yesterday a little bit as well. We can also take the contents of something and direct it into a program using the other arrow. And so program A is going to get its input from a file called input. And lastly, we can use 2 carets, and this is going to append or concatenate the output of program A to this file. And so if I did this, because I've created interactive2 shell, I could echo this, and I'm now appending it to interactive2.shell. I'm going to hit enter. And if I do less interactive2.shell, oh, it only has it once because I did that somewhere else. So I'm going to do it just twice. And now we can see the second time I've done it is added to the end of the file. Hopefully that works. Make sure we're doing okay time-wise. Yeah, so can you specify the output of a program you've already specified the input for? Yeah, you can. That's a good question. And the syntax is using both arrows. So it'd be program like that. So it'd be you're saying you want whatever the input is to go into the program, and you want the output to go into out file. So that's the syntax there. So you can do that, which is nice. So let's practice a little bit. We can do this with a new command that we're going to, I guess, learn in a little bit. There's one called WC, and this stands for word count, not water closet. So if we do word count flag L, and so word count now, I'm adding the modifier to word count that's going to be for lines, large text. And so that, oh, I don't have permission to count it because I took that permission away. Awesome. U plus write large text. So that's what we're doing now. I'm allowing myself now the permission to write large text. This is one other thing I should say about permissions here is the permissions are nested. So if you can execute a file, you can also read and write it. If you can write a file, you can also read it by default. if you can read a file, that's the only thing you can do. So now the standard output of or behavior of the program word count is to display it to the standard output. So we're saying large text has 300 lines because that's what we asked for. We can redirect that to something, I don't know why I called it fls.text, but I did. And now I just get nothing back, which means it ran successfully. I can now look what's in there, and the output of what I redirected is the output of the program word count. I can do ls, and this is list, remember? fls.text, if I hit enter, and then I had what's there, what have we done? We've listed everything that's in the current directory and written it to the file fls.text, but because we used only a single caret, what we've done is we've overwritten what we previously wrote to fls.text. If we want to append that, we can we could do, or if we wanted to redirect that, we could actually do this kind of a couple times, and we should be able to repeat ourselves. And we've taken the head of fls.text and we've appended it to the file here that was already there, right? And so that's what we've done. We've now kind of doubled what's in that file using that append, right? And so hopefully that kind of makes pretty good sense. Make sure we're caught up. Okay. Yep. All right, so I'm going to give us a second to catch up. Hopefully that works. I know, as we're all trying to type along, it can take a second, especially if you got a typo in there. So that's kind of how you redirect the output of a program to something else. And so, maybe I wasn't specific about it enough before. Things like WC or head or ls, although they kind of seem like commands, they really are just little programs that are written and come standard in the Unix operating system. Another really nice thing, other than a redirect, is a pipe. And so a pipe allows you to take the output of one program and feed it into another program. And so program A's output, by using this pipe character, will become program B's input. And this is really nice because you can string a whole bunch of commands together to not have to create a bunch of intermediate files, for example. And so this is analogous to saying program A, redirect it to a file called temp, and then use temp as the input for program B. All right. Oh, yeah. I'll try to. All right. And so we already kind of saw the behavior of the command WC. It's kind of the next one we're going to work with. So this command is to count characters, words, or lines in a file. And so the standard syntax is WC, a file name. And if we type that, so for example, on large text, and before I was specifying lines because I gave it that flag, so I got a little bit ahead of ourselves. So here I just typed WC large text. And what it tells us is the first column is the number of lines. The second column is the number of words. And the last column is the number of characters that are there. And so large text has 1,092 characters, 300 lines, and 300 words. ¿Qué dice?
¿Cómo estamos? Me habló para decirme, papi, ya comprobé que a ti sí te dio el coronavirus. Le dijo,
sorry.
Sí, porque todos los síntomas.
All right. So, let's kind of practice. Let's run through this. And kind of see pipes and WC. So we've already, that should be WC large text, not test text. Sorry, it's an error. So if we do WC large.text, we see that behavior that we asked for before. We can do WC flag L for lines. And that's large text. And again, I'm not that fast of a typer because we don't have that much in this directory. I'm using tab to autocomplete large text. So WC flag L, I'm typing, and then I start off with LA and then hit tab and it autocompletes there for me. So now I know large text has 300 lines. If we wanted to find out what else WC could do for us, we would do what? We'd use the command man and WC. And so this is going to bring up the manual for WC. And then it tells us a bunch of options, right? So I could ask for the number of bytes in a file. I could ask for the number of characters only, the number of lines. I could ask for it to specify kind of files. I could ask for words only. I could ask for the max line length. Maybe that's kind of useful. And that's it. So those are all the things WC can do for me. And I used quit to get out of that manual, or Q, sorry. I hit Q, and I think on Hoffman, there's a couple versions of WC, so you hit Q twice. So Q, and then it gave me another manual, Q. So if we want to learn that pipe command, we could do ls, and this is going to list my directory contents, but I'm going to pipe it into WC minus L. And in this case, I have 7 things in my directory test. And we've done that with this pipe command. And the pipe is over, it's the shift backslash up by your backspace or above your enter, if you're looking for it on your keyboard. And so that's kind of nice, hopefully. Another nice command is the command cat, and cat is short for concatenate, and it concatenates files together and displays them in a terminal. And so we could see that behavior, and so we could do, and we've seen this before. It just prints the standard behavior is to print the file contents to the standard output. So I can do cat large.text, for example, and it's displayed all 300 lines that are in large.text. I could do cat large text and FLS text. And then I could, I'll just type it first that one time, and we can see it's displayed everything to the output, standard output, and it's all 300 lines plus the contents of FLS. If we wanted to know how many lines together we had there, and so I'm going to use my up arrow, because remember my up arrow allows me to get my last command I typed. I could pipe this, the concatenation of both of those files into word count minus line. And it'll tell me total, those 2 files have 314 lines. Kind of nice. I think I got rid of test.text. That's okay. So if I wanted to, I could cat large.text and fls.text, and I could redirect that to a new file we'll call all.text, and nothing got displayed to standard output. But we could, tail that And here I'm using the command tail again to see the bottom of a file. I'm asking for the last 3 lines. And we can see these are the last 3 lines of all.txt, which are the last 3 lines of fls.txt. Hopefully that seems okay. Another really nice thing, especially if you have lots and lots of files, is the command find. And how it works is it works just like this. You type find, you maybe tell it, see what all we have here. Okay, so I just typed ls to display the output, make sure we're on key. So I'm saying find, and then I'm asking for a directory, and here I'm asking for in new. And I'm gonna say flag name. So now I'm asking for test.txt in the directory new, and I'm specifying that I'm asking for type F. I'm asking for a file. And if I hit enter, nothing came up because probably, let me see, oh yeah, I got rid of test.txt yesterday. So I just seen what was in there. So then I did use the up arrow a couple times, right? I should have test2.txt there. So I went through and edited that and hit enter, and it's telling me in new, there is test2.txt. And so that kind of, I know that's a very kind of easy example, but you can really use this to find things, you know, in, for example, your home directory, which is kind of nice. And it will tell you the relative path from where you're asking for your directory of where that file might be. And so that's hopefully pretty nice. Let's check, make sure we're okay. All right, looking good. And so now we're going to kind of move a little bit away from, you know, I think so far, hopefully we're pretty comfortable navigating the Unix file system. And we're going to move away from hopefully trying to think, you know, like we're working in Microsoft Office, we're not using Excel, we're not using, or how we think about using Excel, we're going to, you're think about using Word or think about using PowerPoint. We're going to try to think about how we're going to manipulate things more like a programmer. And so that's kind of where we're leading, and hopefully, you know, we're going to start seeing some of the power of what we can do in this system and learning kind of more complicated, maybe exciting commands. So the first of these is going to be Grep, and it doesn't maybe sound very intuitive, but it stands for global search, a regular expression, and print. And we'll talk more about what regular expressions are in a minute. It allows you to search one or more files for something that contains a certain string. And there's lots of options. Some of the most useful ones are grep flag v, and this is going to list lines that don't contain a string. We can ask for the line numbers, so flag n, where something occurs. We can ask for the number of lines of the string, so now we're counting matches with a flag c. We can ask for file names where a string occurs. This is pretty useful. So what if we had a whole bunch of text files and we wanted to know which ones contained a specific name, for example? We can use flag I. And if we want to make the match case insensitive, it's flag little I. And so grep kind of standard syntax is to treat the first argument you're writing as the pattern you want to match, and everything else that follows as files that it's supposed to look for. If we're okay. Oh yeah, so that's maybe good. So there's a couple good questions. What will happen if you use find and you have new in 2 different directories? Will it show both paths? No, so that's a good question about find. So find is relative to where you're at. And so that, remember, is talking about absolute versus relative paths. So I don't think it would work that way because you can't have 2 directories in the same place that are named the same thing. So that's a good question. And then someone else asked, what's the difference between find and grep? So find is looking for files or directories. Grep is looking at the contents of a file. And so we're not looking for a file name anymore. We're looking at what's contained within that file itself. And hopefully we'll kind of see more of that as we kind of practice a little bit. Let's just kind of start off. Make sure you have large.txt still. So if we type grep, and now we're asking for the match 1 in large.txt, and the output is going to be every line in large text that has a 1 in it, because every line matched every line with a 1 matched my expression, and my expression, or my regular expression, was what I put in the quote. Hopefully that works. We can ask for a little bit more information about that. We can use grep -n, and so now I'm asking for the number, the line number where the match occurs, as well as the match. And the standard output is to say, on line 291, I matched with the expression 291 because 291 had a 1 in it. We can, and I did an up arrow there, and now I'm scrolling back because I didn't want to type that whole thing out again. We can use the C, and this is going to count how many times we match. So in large text, there are 300 or 138 lines that have a 1 in them. And we can feed it multiple files if we want, or we could ask which files contain a match. Sorry, that's the next one I was going to do. And so now I did the up arrow again, and now I'm doing grep. It's it's flag a lowercase l, not or lowercase l, not capital I. And I can ask in these two files which one has a 1, and it tells me large.txt contains a 1, and so FLS, I know, doesn't have a 1 in it. And if I fed it more than one file, the standard behavior here, and so I just deleted that flag. I deleted that flag L. The standard behavior now is to tell me large text has a match for my expression, and what all those matches are. If we remember, we created that file all.txt, and so I used my up arrow again, where I concatenated large and FLS. Now I can see it's telling me that all.txt has a match and what it is. And if I scroll up enough, I can see large.txt has a match and what it is as well. So hopefully that's kind of useful. Although maybe we're already beginning to see, oh shoot, maybe I only wanted to match lines that had exactly the character 1, not the line 281 and 291, et cetera, et cetera. And so we're going to get into how to be more specific with these expressions. So, and we'll kind of talk more about this. And so, maybe here's a little bit of biology now. So if we change directories into the intro to Unix file, or intro to Unix directory, I mean. And so remember, I gave us a bunch of stuff. In here, a couple of things I gave us are HG19 GTF. And so this is a version of the human genome, and this is a GTF file. What is a GTF file? This isn't really important, but if people care, it's a gene transfer format file. And so it's information about gene structure that some people use to annotate genes, for example. So maybe I wanted to get all the annotations from the human genome that belong on chromosome 2. And so now we're, after a day and a half, we're getting into actual biology. Hooray. We could do that. So I'm grepping the expression chromosome 2 in HG19 GTF, and I'm going to redirect the output to chromosome2.txt. I'll hit enter. It operated pretty quickly. Hopefully we feel good about that. Make sure we're all okay. Yep, so good, all right. I think we're good. And so that's good. Hopefully now we have everything that's in that GTF file. So if we head, make sure I'm right. We head chromosome 2, and so we just created this chromosome 2 text file. We can see here we're text wrapping, but it starts off with chromosome 2, HG19, known gene. It gives you something about the gene kind of annotation, where it's from. It tells you an exon. It tells you positions for it. It tells you a gene ID, and then it goes on to the next one. I mean, it's not that important what's actually in it, but that's what we have. We're feeling maybe good about ourselves. Let's tail this file, though. And if we tail the file, we see we've done the same thing that we did before when we were looking for 1 with grep, except for we've now grabbed every instance of chromosome 21, because chromosome 21 contains the expression chromosome 2. And so that's kind of unfortunate. But we can potentially do things that'll help us out here, using more specific expressions to specify exactly what match we want grep to behave with. And these are called regular expressions. And these are basically just strings that can be used to describe specific sequences of characters. And since we've been going for almost an hour and we're about to get into a complete kind of new subject, how do we feel about taking a couple-minute break and then grabbing coffee, and then we kind of get into regular expressions and hopefully take off with useful stuff. So it's 9:55, so let's kind of try to get back at 10 once we get our coffee refilled, and then we'll kind of get into regular expressions. All right. So let's get back to it. A few folks had a couple good questions. One is, does the quote matter? Does it matter if I do a single quote or a double quote? And so that would be, if I'm grepping chromosome 2 in HG19 GTF, it does not matter. So some commands are particular and they necessitate that you use either a single quote or a double quote. In this case, grep is friendly to us. It doesn't matter. And so that's what happened when I typed it. And then someone else was asking again, so why, when I type grep chromosome 2 in HG19 GTF, do I also match chromosome 21? And it's because chromosome 2 is contained within chromosome 21. And so we can make our expression more specific if we want to. So we can, hopefully have exact matches or make our matches exact as possible to be useful to us. So we can do those using these things called regular expressions. And are we all kind of back, hopefully, or getting back? All right. And so we can use those using these things called regular expressions. And we can learn kind of how to be as specific as possible using regular expressions. And so a regular expression would be just like we used before. Chromosome 2 is an example of a regular expression. And so if my regular expression is CKS, I would match Unix tools rock. If this was a line, I would also match the line Unix tools suck, and I would miss the line Unix tools are okay. And so because my regular expression isn't specific enough, even though I only potentially wanted Unix tools rock, I'm also getting the line that says Unix tools suck. So they can also match a string in more than one place. So, I could match Scrapple and Apple. Scrapple is a funny kind of meat loaf type food item. And so if I only wanted to match Apple, I would also match Scrapple here. And actually the behavior of grep, the default behavior is to search a line until it hits a match and then prints that to standard output or redirects it as you want to. So if this was my line and I was searching for the regular expression Apple, my match would actually be Scrapple. We can use special tools or special symbols in our regular expression. So for example, a period can be used to match any character within a regular expression. And so O period space would match for and fool, because it doesn't matter what comes after the O. As long as there's an O, something, and a space, we will match that line. We can also use character classes, and we can specify those in square brackets, and they'll match any character that's contained within those square brackets. So B square bracket EOR AT will match beat, will match brat, or will match boat. So all three of those match. Any of those will match, and that's good. And so that's potentially also useful. We can use the up arrow within the character class to not match what comes after that. And so B in our square brackets now only, up arrow EO will not match beat or boat, but will only match brat, because it would match any character other than E or O where the R is in that second character. So hopefully that's, a start. And so we can practice on these. Make sure we're doing okay. And so I've given us in the intro to Unix directory a file called regex.txt. So it's right here. And if we wanted to see what was in it, for example, I could less regex.txt, and we can see it's just a list of a bunch of B words. So we could grep, and you can see what I did there was because we need to always make sure we close our quotes, I typed 2 sets of quotes and then use my arrow to go back one. That's kind of old R syntax from before. If you're used to using R, the kind of programming statistical language, now if you type a single quote, it actually closes the quote for you because it got smart. But for a long time it didn't. And so it's kind of got used to doing that. So if I type grep boat in regex.txt, it returned boat. Great. Make sure yep. Yeah, it's something also important, I think. So yeah, so someone was asking, are regular expressions case sensitive? And they are. Although we remember there's lots and lots of things we could do with grep. And one of those would be the command for case insensitivity. I can't remember if do we do that? I don't think we use that example, so we'll just do it now. Sorry, scrolling ahead. So if we wanted to figure out all the things we could do with grep, we would look at the manual for grep. and it searches the named input files and it tells us what it does. And then it tells us there's E and F grep, which we'll talk about a little bit later. And we can use different flags. We're going to learn about some of these in a little bit. But we have the lowercase I flag, which is ignore case. And so this will match the pattern depending on if it's uppercase or lowercase. So it ignores the case sensitivity. So that's kind of nice. And then I use quit to get out of that. So just for a fun example, or just to do it, I guess, if I grep to capital BOAT in regular expression, I get nothing back because there's no matches. If I do an up arrow, so I get that command again, and I add the case insensitivity flag, I get boat back. And it displays it not as the match in caps, but it displays it as the match as it appears in the file. So hopefully that's helpful. So we could use grep, and now we're using character classes, EOR, AT, in regular expression.text. We hit enter, and we get beat, brat, and boat, just like we thought we would. I use the up arrow again because I don't want to type that all out. Now I'm grepping B, any character, in A and T. And we get the same thing because those are the only matches in that file. I'm going to use the up arrow twice to get back to that character class. And we are going to negate any of those. And so this is going to be Shift 6 for that up arrow, if you're not used to where that is. And now we're going to match anything that occurs after a B and before AT, except for EO or R. And there's no matches there. I'm going to use my up arrow. I'm going to delete the AT. And so we're going to now match any letter in the file regex, or any word in the file regex.text that has a B followed by a character, and that character can be anything other than EO or R. And so I get bat and banana. And so, you know, what you've maybe noticed is I've just kind of been verbalizing or talking through these commands. And that's kind of the really nice thing about all of these Unix commands is basically if I can verbalize what I want the thing to do, I can type it out. And so hopefully that's pretty helpful. You know, I want to match anything that starts specifically with, you know, chromosome 2. How do I find that? And then we can actually, you know, learn how to do that. Oh, yeah, and you can put any anything goes in that character class, and we'll learn more about what we can fit in that character class here in a minute. Okay, so more about character classes. Yep, that's a good question, or timely. We can match anything we want to put in there. So, you know, A, E, I, O, or U will match any of those characters. I can be specific about a specific case in a specific spot. So lowercase k, uppercase k will match corn or corn. We can also specify ranges in those character classes in kind of alphanumerically sensical ways. So 1 through 9 is the same thing as 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E is the same thing as A through E. And we can put multiple ranges in there as well. So if I wanted to match anything that was A through E and 1 through 9, I could type it all out, or I could say AE19. And the dash character has that special meaning, but only within inside of 2 other characters within a normal range. So dash 1, 2, 3 would match a dash, a 1, a 2, or a 3. And that's different than saying 1 dash 3, which would match 1, 2, or 3, and not that dash. see if we're, make sure. Yeah, so A, B, C, D, E is the equivalent as A through E. And they have to be in order in range, so you can't kind of like skip around and do weird stuff. It's not perfect, but it has to be kind of alphanumerically in order in the alphabet. There's different also ways to specify any alphanumeric characters. So I could say A through Z, and A through Z would give me any letter that is in the alphabet, and it would not matter if it's case sensitive or not. I can use a special double bracket character class and specify within with these colons that I want something to be alpha. Although if we notice, this is actually shorter to type than typing out alpha. The same thing, we can do digits. So any digit is 0 through 9. Or we could type, double square bracket colon digit, which it's also then much shorter to type 0 through 9 in this situation. And we can match any alphanumeric character. And this is the only time using this character class shortcut. Alphanumeric, all num, is shorter than typing out the other character expression that would go with inside of it. And then lastly, this is pretty nice, is we can use anchors, and they will go outside of that character class, because here the up arrow can mean a couple things. Up arrow means at the beginning of a line, and the $ means at the end of the line. And so we're specifying where in a file we expect something to see. And if we put this up arrow inside of the square brackets, remember we're negating anything we're using. If it comes before the square brackets or before at the beginning of our expression, it means that expression has to be at the beginning of a file. So up arrow BEORAT would match beat, because beat is at the beginning of a line. B character class EORAT $ would only match boat, because the line ends with boat. So we have to put the special expression at the beginning or end of our regular expression we want to match. So maybe we can kind of practice this and see, what we think we're doing. Yeah, and then just, to follow up with someone else's question here. Yep, so -123 matches dash as a character. It wouldn't be -1, -2, -3. Yep, it matches dash as a specific character in that character class. And so we have a couple regular expression files, and we can, verbalize or talk these through, just like I was saying. So for example, this first one, grep, and now my regular expression's coming inside the quotes again. You always have to do that. And I can have a character class, A in capital or lowercase 1 will match any line that has an A, regardless of its case followed by a 1. So we can check that out, make sure it works. And we're going to now work on a file called regular expression 2. And we can see I've matched A1 lowercase, A1 uppercase, and A1 at uppercase, but in the second column here. Here, I'm going to put the up arrow in front of the character class. And so what's this going to do is this is going to match, because it's outside of the character class, this is going to match any line that starts with an A, capital or lowercase, followed by a 1. And so that's what we have here. I could join character classes. So here, I just want to type curly brackets. I'm going to match anytime we have an A followed by a number, any number. And then I guess my code is more expressive here. And that number anchors the end of a line. So now we can see we're matching this A1 and this A3 because they're following at the end of the line. Just gonna up arrow to delete a couple things. And now I'm getting any line that has a number on it. And although it's probably not the most sensical thing to put here because of how it is, specifically in this set of code, here I'm going to match any line that has a character. This is what we're saying because we don't have anything else specified about this character class. So any line that has a character that's a number or a letter. So I guess the line could have characters that were all symbols and they wouldn't match. And that's what we get here. And this match is just asking for any alphabetical character. And so if we have a line up here, like you can see, that has 1, 2, 3, 4, we shouldn't get that matched line. And we don't. It just matches any line that has a character that is a letter. And it doesn't matter the case. Yep. And we do need the quotes around the character classes. That's a fact. Yeah, so Grep is expecting a regular expression that's coming in quotes. And the special character classes, if we're specifying them, need to have the double brackets. If we did this without the double brackets, I believe it would match any instance of a colon, an A, L, an a U, or an M. And then a colon, again, is actually, in this case, would just be redundant in this situation. And so without those double brackets, it doesn't know that we're giving it a special character class. And then we've learned a little bit about asterisks. So asterisks are really useful in regular expressions as well, because they allow for repetition operators. So an asterisk is kind of a wild card. It matches 0 or more occurrences of the preceding character, so the character that comes before it. So if the regular expression is y asterisk y, we'd match 0 or more occurrences of a. We'd match any time where there's a y with something and a y. So that's the same way here. I'm showing, I could say I want my regular expression to be O, A, asterisk O. I don't even have to have an A there. I can match 0 or more occurrences of the A. So this regular expression, O, A, asterisk O, would match fool, or any instance where you had a O and 1 or more A's followed by an O. It would match both of those just fine. Hopefully that seems okay. And then we learned a little bit about this when we made our large text file, is special characters. And these are going to be backslashes followed by a symbol. And so this could be a space or a tab, or S with a plus for many spaces, or 2 tabs, or the one we learned when we made that large text file was a \n for a new line. And so these are special characters that are actually in our files. They're there. they're just not displayed to the screen. And so there's different syntax and different, Windows has a little bit different syntax than Unix. But when you hit return, for example, when you're typing something, it's adding a \n there. It just understands that \n means what comes next is on the next line. So we had, kind of went through this whole regular expression deal because we had this situation where we had grep. We tried to grep lines that corresponded to chromosome 2 in this GTF file. And, if we, again, were to tail that, hopefully we see that the last line there doesn't have chromosome 2, but has chromosome 21, because chromosome 2 is contained within chromosome 21. So hopefully, we could all think up a number of ways where we could match only lines that matched chromosome 2 and not chromosome 21, for example, now. And that's kind of hopefully the goal. All right, cool. I think we're good. All right, so, we could do that now. Hopefully we've learned. We could do that in a number of ways. We could add a space there. So we could grep, if we understand the format of that GTF file, chromosome 2, space, in HG19 GTF. And now what I'm doing, because I'm not using the double carets, I'm using the single carets, I'm redirecting that to chromosome 2.txt, although here, I guess in my example, I called it GTF. And so now if we tail chromosome 2.txt, we'll see we only have lines that correspond to chromosome 2. Maybe we wanted to be even more specific. And so maybe because this is the gene annotation file, maybe there's some gene on chromosome 6 that's called chromosome 2 like factor or something like that, because that's how folks like to name things that they're not quite sure what they are. We could be even more specific. And I could, if I understand what I know about my file, I could say chromosome 2 has to start the line and then be followed by a space in that GTF file. And so now I'm being more specific with this command. And we just want to double check. So we head that file, we have lines that start with chromosome 2. And if we tail that file, we should have only lines with chromosome 2. So hopefully that seems, relatively useful. And there, we can do specific repetition operators in grep as well. So we've already learned the asterisk is 0 or more. We could have 0 or 1. It could be an optional element, and we could use a question mark. We could use 1 or more. We could use a addition sign, a plus sign for that. We could specify the number of times we expect to see something, and we would put the number within curly brackets. We could ask for some specific instance of, between 2 and 5 times. We want, 2 and 5 A's in yay. We don't want 8 A's. We don't want 2 A's. We could specify that. We could specify at least some expression of, or we could ask for and or operators here. But if we're going to use these special repeat operators, we have to use grep flag capital E. And maybe at some point, if you start Googling around and stuff, you might see people referring to egrep. And egrep and grep flag capital E are the same thing. And just to kind of prove it to you, if we man grep, it will actually tell us here in the description. So grep searches for the named input files, for a pattern. In addition, there are variant programs called egrep and fgrep that are available. Egrep is the same as grep E, fgrep is the same as grep capital F. Direct invocation of egrep or fgrep is depreciated, which means they're no longer kind of supported in the Unix language, but they're provided to kind of allow for historic back compatibility. So folks that need to use them. So if you had a script that's old and it had egrep in it, it would still work. And so there's basically a hidden kind of symbol in grep that allows you to understand that if I type egrep, and there it's actually telling me, what to do. And so here I just typed a command and it says usage egrep options pattern file. And then telling me, here's where I go for help. So at least it's being sort of helpful, but it at least knows that egrep is the same as grep flag E. And so those are the same things. But if we're doing some sort of repetition operator, we need to use those. So let's try this. We can grep flag E, flag capital E. Now I'm going to ask for A1 or B1 in my regular expression 2 text file. And we can see we match this line actually for this match and this line for B1. And so we're matching the first match. If we didn't use that repeat operator, we don't get a match. And the reason why we don't get a match is because there are no lines in regular expression 2 that contain A1, B1, pipe B1, or A1, pipe B1. And so it's actually looking for a line that contains this exact match here without this E flag. And just I did an up arrow there and just to prove that it works the same. egrep gives me the same thing as grep flag big E. And so especially if you're Googling around and stuff, a lot of people were kind of trained on egrep and fgrep and use them kind of standardly. And so there's kind of nothing wrong with using that flag. If you don't have a repeat operator, you just need it there. The same way, I did the up arrow there. I can ask for grep flag capital E, exactly one match of A1. And it'll give me this. I'm going to up arrow. I could, for example, use 2 matches if I wanted to. That's odd. Oh, because it's asking for any specific match of A or 1 there. And hopefully that works. Sure, doing okay. Let's see, yeah. Yeah, so someone was asking, they typed, this is maybe getting a little complicated, but maybe we'll just do it. I think we have the time. So somebody was asking about A B plus C. So they typed this. They got all sorts of stuff. So that's because this regular expression isn't specific enough to just get AA, BBC. And so you can kind of fool around with what you'd need to type. And it's kind of one of those things where this is maybe a good example of how you can be sure what you're doing is what you want. You always want to be as specific as possible with these sorts of things, especially when you're dealing with real data that you actually care about. So it's really nice to actually create for yourself. And this is something I do with my own data. I'll either take, the top, 4,000 lines from a FASTQ or something like that, because if, in the FASTQ file, every sequence is represented by 4 lines. So if I want the first 1,000 sequences, I'll take the first 4,000 lines. Or I'll create myself a little dummy table if I want to make sure I'm modifying something correctly, and I'll run my script on something where I can see the output and see that the output is what I expect before I run that command over something that's really large and crazy. And so, for example, we have that large.txt. If that was what we wanted to do, one way we could get the first 1,000 lines of large.txt would be head, if I wanted just the first 50 lines, minus n50, and large.txt is there. There's one back, and then I'm going to redirect the output to medium.txt or whatever I wanted to call it, right? And so I can do that. Hopefully that works for us. Okay, cool. So yep, so that's just, it's a good kind of lesson to be mindful of what you're doing. I think a few years ago now, probably 5 or 6 years ago now, there's a real famous example of some human geneticists that had to, I think, retract a science paper because they had piped the input of one program into, or the output of one program into the input of another one, and it didn't pipe correctly because there was a formatting issue, and so their output was all wrong, or they hadn't modified the files the way they thought they had. So you don't want to be the people that have to retract your science paper because your code didn't behave like you wanted. And so it can be a useful practice, at least, to get into giving yourself little experimental dummy data sets to play with. So we can do repetition operators using these special notations. So the curly brackets apply to more than just the previous character. So if you want the curly brackets to apply to more than just the previous character, you have to use the normal brackets notation. So these sub-expressions are treated like a single character. So anything that comes within these brackets is going to be treated like a single character that you're going to be acting upon or has to be found in a certain way. So remember, A apostrophe or asterisk matches 0 or more occurrences of A. ABC would match AB, ABC, ABCC, etc. ABC asterisk in brackets, in parentheses here, will match ABC or ABC, 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 etc. It's treating what comes within these brackets as a single character. ABC curly bracket 2, 3 will match exactly 2 or 3 occurrences of ABC together. And so we can be really specific with these things. So let's at least run through, we don't need to run through all these, but let's run through at least some of them so we can kind of see them in action. And we need to use RE parentheses. So grep capital E, A plus. So what we should be doing here, we should be kind of thinking about what we're going to get. So here we're going to get any occurrence of an A at least one time. So it's matched this A, this AA, this A, this AAA. If we want to be specific about how many times we expect A to follow each other, we can do that by specifying a number in curly brackets. So here I'm asking for exactly 3 A's in a row. and I only get the line AAA, I can ask for two, the number lock wasn't on. I can ask for 2 or 3 occurrences of an A. And now I've gotten both of these lines. And we can do things, for example, maybe I don't care about the case. And so I should be able to string that together. I thought there was something in there that had, maybe it won't work with the, no. I thought I had a capital A, lowercase a in there, but maybe I don't. Oh, I don't have one there, so that's why. So we can kind of string them together like that. Let's try ABC in brackets. So I want it to come more than once or more than one time. I could ask for it star. And now what we're doing is we're asking for any occurrence here with the star of ABC that happened 0 or more than one time. And since every line has either ABC once or never, we've matched every line. And so we need to be careful about what we're doing specifically with asterisks versus a plus sign. So the plus sign is asking for 1 or more occurrences of ABC. The asterisk is asking for 0 or more occurrences of ABC. We could ask for it to happen exactly twice. And so now we're matching lines that have ABC, ABC only. Yes, there aren't. I thought there was one. Maybe not. Oh, it's because we are not case insensitive. And so now here we're stringing multiple flags together. We're asking for a specific match that's case insensitive that has ABC twice, specifically twice. So we get ABC, ABC. Make sure we're okay. Yep. So curly brackets, yep, denote the number of times you expect the preceding character to match. And so what we have here, when we're specifying ABC in parentheses, we're saying what comes within these brackets is treated as a single character, and it has to be found twice. However, if I were to type this, now I'd be asking specifically for any time we get A, B, C, C. So A, B, C, C would happen twice. And we don't have that in that file. And we can get really kind of tricky with our regular expressions. So like, what's this one down here going to say for us? We want to grep anytime we see a letter followed by a number twice. And it's because we have these brackets outside of our regular expression. So we can kind of see how these things maybe behave a little bit differently. So if I do this line here, I'm asking for an alphabetical character followed by two numbers, and that's what this expression is asking for. So here I'm grepping, here to the I. So we get on one line, or almost one line. I'm grepping anytime we get an alphabetical character followed by a number, but there's going to be two numbers. And so that doesn't give us a match. However, if I add a bracket here, now I'm asking, I've changed my expression. And so now I'm asking for any time we get a letter followed by a number twice. And so here now we're matching the expression B1A1 because we have a letter, a number, and a letter and a number. And so we can be really specific here. Hopefully that works for us. And the last one, just to kind of talk through, because I think it's useful if we kind of verbalize these. And I did an up arrow again. I'm going to do the one on last line is I'm going to delete the 2. And so now I'm asking specifically for a kind of interesting regular expression. I'm asking for a letter followed by a number, followed by a space, followed by an A. And so here we get a letter, a number, a space, and an A. And so this was my match in this regular expression. Hopefully that seems all right. So we can be really specific with what we want to ask and how we use these things. So this is less fun doing this online. But if we take a moment, could we figure out what this would be? Well, it'd be a phone number. So it's any number that occurred 3 times with a dash that occurred maybe 0 or 1 time, followed by a number that occurred 3 times, followed by a dash that occurred 0 or 1 time, followed by any number that occurred 4 times. And we can see we're being relatively specific about what we're looking for. And so if we look, for example, in, did I not have that? Okay. In less f.text, I've kind of denoted lots of different ways you could give a phone number. And we were very specific in our grep expression there. So we're only going to get 4 numbers that are formatted in some ways. Yeah. So any number that occurred 3 times. Now I want a dash that can occur exactly zero or once. It's going to be followed by any number that occurred 0 or once, followed by any number, any number that occurred 3 times. Oops. Followed by a dash. There we are. That occurred 0 or once, followed by any number that occurs 4 times. And of course, I put a typo in there somewhere. Oh, that's what I did. So this is why it's nice when you can use the up arrow. I put a number, not a dash there. You still didn't do it right. Oh, and then I put a dash in the wrong place there. The joy of having people watch you type. And so we match phone numbers that occur with dashes or without dashes, just straight. All right. So I'm going to vote that we're going to actually, let's take another 5-minute break here before we get into SED, both because it's kind of a good subject break and also because my dog is whining horribly at me and needs to get put on the patio. So let's do that. And then we'll be back in, let's try to get back at like 3 till 11. And we'll kind of talk about some stream editing, which is our nice version of search and replace. So somebody I was kind of scrolling through the chats had a good question, and this is something that's probably useful for, or potentially useful for lots of folks, is can you use a string or a file as your matching pattern for a grep? And you can with the flag F file. And so it obtains patterns from a file, 1 per line. And so you can specify, you know, if you had a list of things, if you wanted to match chromosome 3, chromosome 6, and chromosome 9, you could, you know, have a file that had chromosome 3, chromosome 6, chromosome 9, all in one line, and feed grep that file, and it should work for you. So hopefully that's helpful. Hopefully our folks are joining us back. All right. There we are. Let's see. So that hopefully is helpful. And then I'll quit that out. So now we're going to learn kind of our last main command for today. And I know maybe for folks that want to get like, you know, crazy into stuff, we will get to points where this is all hopefully very useful after a while. It just kind of, you know, we're building lots of blocks, we're putting things together. The next command we're going to use is sed, and sed stands for stream editor. And it's a non-interactive text editor. So it's a line that basically acts like find and replace in your Microsoft Office suite. And so why do this as opposed to, you know, find and replace or something like that? And generally, it's because, you know, we're going to end up having files that are oftentimes very, very large, and you don't necessarily want to, you know, use find and replace. You don't want to try to open up something in Excel. Maybe you have a file that's larger than Excel can even handle. And sed, if you have a tab delimited file, for example, is way, way faster than opening up some spreadsheet in Excel and doing a find and replace. And so the text flows as input through sed, is modified and directed to the standard output. And so you add sed, give it a list of options, just like lots of other things, whatever command you want sed to do. And so you tell sed a command, and then you feed it a file to edit. Oh, so like I said, sed's really useful for kind of 3 cases. Files are too large. Editing's too complicated for a regular text editor. So we can feed sed all sorts of crazy regular expressions. And you want to do multiple edits in one pass. You can use sed as well. Or you could edit lots and lots of files all at once as well. So these are all nice things we can do. And you're kind of like, yeah, is this really useful? Yeah, you're gonna have files that are, you know, maybe 30 gigs or something. They won't even open in a text editor. So the first kind of main thing we can do with sed is the substitute command. And so the syntax here is going to be sed quote. And here, I don't think it matters if it's single or double quote. Well, we can test it if we're not sure. We're going to do an S, a slash, the old word, a slash, the new word, and then we'll end our quote. And then the file we want to edit. Make sure this is good. Okay. And so that's, you know, one thing we can do. So we should have, we'll look at it, a file called to be text, and it has to be or not to be, but here we're talking about insects and not Shakespeare. So maybe we want to fix this, and so we can use sed to do this for us. And we'll do s. We want to replace b with b in the file to be dot text. We hit enter, and we've noticed, we just get standard output directed, and so we've only, so we haven't saved this anywhere else, and we've only modified the first instance of BEE. And the reason why is because sed's default behavior is to find the first match on a line, edit it, and then move on to the next line. And just to make sure if folks are used to double quotes, I deleted there we are. It also works. Yep. So I did not lie to you. You can use single quotes and or double quotes. So we can add something here, and this is going to be the global match option. And so this will come after our last slash. And this is telling it not to move on once it hits that first match. So I did my up arrow now, and I've added a G to that command. And now I've fixed both instances of BEE, because this G following this last slash is telling sed to be global, which means once we hit the first match on a line, keep going through the rest of that line. Don't stop after the first match and move on to the next line. And so that's exactly what we're asking for. That's good. We'll kind of get there. Yeah, someone was asking about specifying lines. You can, I don't think you can do it in sed. I think you'd probably want to do something like some sort of crafty pipe where you're picking certain lines from a file and then redirecting them through sed. So you'd be like, head, the first 10 lines, and then pipe that into sed, for example. And you can do kind of different combinations of head and tail to get line strings. Although I'm not positive. I've never tried that in sed, so I'm not sure. So I just opened up the manual. I was going to look at it and see if there's anything about lines really quickly. Yeah, so that's a line length wrap. I'm not sure. And I'm honestly not sure if you could do that or not. Maybe someone else chimed in. Okay, cool. Yep, so I'm honestly not sure about the lines thing. That's honestly if I needed to do it, I would, knowing sed is the tool I want, I would Google it. We can also edit a matched text. So sed has an E command as well. And so if we wanted to match a pattern and do something to edit it, we could, for example, put a parentheses around it. So here, this sed script would find whatever our pattern was and bracket it in our file. And so we can kind of see a couple examples of different things we can do here. And so hopefully we've kind of followed along with our to be's and learn the global command. We can do multiple fixes in one pass. So we can pipe sed into the next sed if we wanted to. So here I'm going to search for 7 and replace it with 9 globally in file underscore sed, which you should have. And then I'm going to pipe that into sed again. And I'm going to search for 9 and replace it with 2 globally. And so now what I'm doing is I'm taking every instance of 7 and changing it to 9. And now every instance of 9, I'm changing it to 2. And so 7s and 9s in this file should both be changed to 2. And so 4 score and 2 years ago. If this was a file with multiple instances of 7 and 9, that's what we could do. We can be very specific with our seds. So maybe I wanted to ask one of the up arrow there. I wanted to change, I'll type it out so we're not, just so we can see what's there in file. Said it's 4 score and 7 years ago. So maybe I wanted to change the and to or, so 4 score or 7 years ago. I could do that with said substitute and or globally in file said. And now I have 4 score or 7 years ago. But just like in grep, I can modify things. So I could use a modifier and only change or and to or if and occurs at the beginning of a line, for example. And so now I don't match and, because and isn't at the beginning of a line, it won't substitute it out. Let's see if folks. Okay. So I think we're good. So you can also use, different sorts of character matches like we learned about in grep. So I could do sed substitute s ... for XXXXX or whatever it wanted to be globally. And so this is going to match any line that has starts, or any word that starts with an S and has exactly 4 more characters. And so now we've done that. And we can see the behavior here is we've matched score, 7, and also S space AGL. So all those matched. We can do something maybe kind of fun if we wanted to play with symbols. This would work. We could say a go at the end of a line and change it to a go exclamation mark. And so now we haven't matched a go $, we've matched a go at the end of a line to change it to a go exclamation mark. And then, we can do things with character classes like we were using before. So we could sed substitute out, for example, a 1 or a 2 for a 3 globally. And then we're going to go to regular expression 2.text. And so now we've taken any instance of 1 or 2 and substituted it for a 3. The same way we could substitute any alphanumeric character or any alphabetic character, for example, for a capital B, and it prints it to the standard output. And then the last thing is we could add parentheses, or we can modify the text through through sed. And so here we need to use capital E. And so now we're going to substitute any alphanumeric character that occurs exactly twice by adding a parentheses around it. And so now we can see anytime we have an alphanumeric character that's happened exactly twice, we've put a parentheses around it. And the behavior here for the AAA and the ABC is actually to leave them off. But ABCA, ABC got 3 parentheses around it because it just worked in order globally. If we didn't include the global, it would just get the first match for those. Yep. So folks are asking. Yep. So remember, all of our programs that we're using. So sed's a program, grep's a program. The default behavior is to display something to the standard output, and that's to the screen. It just prints it to the screen. And so that was a good question. Is it doesn't actually modify the file? No, it doesn't modify the file. And so if we wanted to modify the file, we would have to either redirect a file to something else using a caret. So if we wanted to add those parentheses and keep them, I'm just going to call this new sed.text, for example. And then I could less into new sed.text, and now I've saved it. Or we could maybe think about what we want to do. And so if we wanted to, I was going to see if we, all right, yep, we don't. So if we wanted to think about if there's an option that we could use, there is, and we could manual sed to check, although I know what it is, it's I. And so I means do it in place. So edits the files in place. And that's exactly what you do. And so you can edit that file on the fly. The thing you want to be careful about using sed flag I, let's go up to like the 2B ones or something. There we are. So if I wanted to edit 2B and have it permanent, I would do it just like this. So flag I, sed flag I, substitute BEE for BE globally in that file, and it'll edit it. The thing we want to be careful about when we're doing that is that those changes are permanent, and so we can never go back. If we have a regular expression that's not perfect, then it'll edit every instance of it. And so we've maybe seen, maybe the reason why we got BEE in our file in the first place is we wanted to, we realized, we had typed something wrong and had a situation where there's a E and we want it to be EE, and it substituted every instance of that. So, if this was our expression, it actually now will change every instance of E to an EE, no matter where that occurs. And so we can kind of see what that would look like. And so now it's changed every E to a double E, and it's gone even more haywire because it's changed, every E that was in 2B to double E's here. And so you can kind of see how if you're not really careful about what you're doing, you can kind of get do bad things to your original file if you care about your original file. So you want to, as long as you can use the I if you're sure what you're doing is correct. The other thing that's really important to do with sed is we can redirect, and that's the correct thing to do. You know, like I was saying, it's or maybe better than you know, modifying your original file, but you don't want to read and write over the same file. And the reason why is because the default behavior of everything in Unix with redirections is to basically create the file before you run the program. So if you have a redirection, the first thing you do is you create that new file, and it's blank. So if you had this command, you know, sed substitute 7.9 sed file, and you're redirecting it to sed file, the first thing this whole line's doing is creating an empty file called sed file, and then acting on that empty file and writing the output to itself. And so there's nothing there to work on. And so you'd erase everything you have. So you want to be careful with that. We can also delete lines with sed, or delete lines that contain strings. And we're going to use the D modifier. And so we could do that, for example, if we do just, okay. Do not give us that. Oh yeah, medium. We'll use the medium.txt or large.txt. So for example, we could do sed, and here we're going to 3D is going to delete the third line of med.txt. And I guess I made med.txt. Remember, I did that a minute ago, or an hour ago maybe. And so what I did was I did head. I'll just do -n10 so we can display the output. And if we're in Intro to Unix back one directory, we should have large text, and we'll create med for medium .txt. So we can create that file. So if we less that, it should have the numbers 1 through 10 in it. And so I could do sed 3D medium.txt. And now I've deleted the third line. So maybe this is something useful. You could remove a line that contains a string. And here we're going to use those brackets. So maybe I wanted to delete every line that has a 7 on it. This would be the code. Within, we're finding 7. This is our pattern to match, and we're deleting it in our medium.txt file. And so now I've deleted 7. Or you could delete, for example, the last line if you wanted to. And here we're going to use our anchors, but it's a little bit different. So you could delete our last line, or and so now we have just 1 through 9. Maybe that's useful. I guess it doesn't it won't do the first line. And so maybe that's kind of useful if we want to get rid of lines, for example. And I guess here's a little bit more practice if we want to, you know, run through 1 or 2 of them. So we could, in our regular expression 2.txt file, you know, we could delete any line that has an A, or we could delete any line with a number. So here, I'm matching any line with a number, and I'm deleting it in regular expression 2.txt. And so now all I have are completely alphabetic characters, for example. So maybe that's something useful for us. All right. I guess we're going a little bit faster as well, but I'm going to show us one other cool thing after kind of our daily summary. So today, hopefully we feel comfortable about file permissions. Hopefully we feel that we've learned the tools or commands cat and world count and how to redirect things, how to pipe files from one to the, or how to pipe output from one program into the input of a next file, how to create symbolic links. We did that yesterday maybe. And we learned about grep, regular expressions, and sed. One other thing I wanted to show us is just like we can edit, and this is going to be up for you if you want to do this. Just like we can edit our bash profile on Hoffman, we can edit the behavior of our own computers as well. If I don't want to have to type the whole SSH, pscot17 at Hoffman 2 with the whole address. So we can edit our bash profiles on our own personal computers if we want to. And we can do that if we have a Unix or a Mac machine. And if we're using Cygwin or something else, you can also create a shortcut. And this is something, if you want to do this or you feel comfortable with it, you're more than welcome to. I'm not going to force you. And just remember, your personal bash profiles can be, you want to be nice to them if you can mess up your stuff or how your computer operates if you do something wacky with them. But before we do that, I just want to remind us, so we're on an interactive node right now. This number is going to be different for you than it is for me probably, but this is where I'm at on the computational node. Once we're done with this interactive session, if I want to close it, I type exit, and that first exit, now I'm back into the login node. And if I want to log off Hoffman, I think we should have probably done this yesterday and I forgot to, I type exit again, and now my connection to Hoffman's closed and I'm back home. If I want to close this terminal, I'd type exit a third time, but I'm not going to quite yet. I'm gonna see what all right, I think we're just, folks are playing around there. So I think we'll wait, or that'll be fine. So that's that. So if you're on a Mac or a Linux machine, now on your own computer, you could do CD tilde, and that should take you home. And you can open your own bash profile. You could do it in terminal using nano period bash underscore profile. And just like we added an alias for RM or CD or whatever else to our Hoffman accounts, we can add an alias to our own computer. And I've done this on my own computer. And what you type is in that bash profile, the lines alias, and then whatever you want to call Hoffman. And then you give it an equal sign, and then you tell it the whole path to log into Hoffman. And then you would source your bash profile or restart your computer, just like we would have done on our own computers. And what this allows us to do is, we type this whole thing to log in. And now if I added this line to my bash profile, I just type SSH Hoffman, and it'll give me the same behavior as if I typed that whole thing. So my computer has an alias set up for it. And then I would type my password just like before. And, hopefully I typo my password, of course, and then I log in. And so we can set up aliases on our own computers as well to save time when we're typing these sorts of things. I'm going to log back off again. And probably, folks have noticed if they're using Cygwin, I'm also using Cygwin, which means I'm not on a Mac or a Linux machine. I'm on a Windows machine. And we can do the same thing there. It's a little bit different. But what you do is you would go on your home directory. So on your computer, you would open up in a text editor. And it's really important here, this is a text editor. This isn't going to be Office or something else. This isn't going to be, it's not going to be Microsoft Word or anything else like that. You're going to want to have a text editor. So you're going to want to be in like Notepad. and you're going to open a file that's called SSH config. That's going to be located in the path will be this PC. It'll be Windows C, wherever you've installed Cygwin. In that Cygwin folder, there's going to be a folder called etc. And this SSH config should be there. And at the end of that, you're going to add these 4 lines. And this is going to be host, and this is going to be Hoffman. It'll be whatever you want to call Hoffman. This will be what you'll call. And so just like I type SSH Hoffman, it's because this is what I've named Hoffman. And then it's important that these 3 things are tabbed in. You have the host name, and this is going to be the address where Hoffman is. Port, and we're telling it what the port is. It's 22, and that's the correct port for Hoffman. And then the user would be whatever your username is. So in my case, it's pscott17. And then you'd restart Cygwin, and then you should be able to log in just like this. And if you could, yeah, I'm typing too quickly for my password. And then that should get us somewhere nice. So I wanted to share that with you just because it's kind of maybe helpful. So we don't have to type that whole thing out all the time. Just like kind of showing us that we could create a little script for interactive shell that we'll talk about using tomorrow. So hopefully that was relatively useful. I guess we're a little early again, but I'm happy to stick around and help folks with things. So tomorrow we're going to get really into more advanced kind of programming stuff, how to write shell scripts, which are scripts that are going to contain a bunch of commands, and things like for loops, so how to perform the same commands on a bunch of different files. And then lastly, how to get into submitting jobs on Hoffman, which makes us feel good because when we submit jobs, then they're just kind of waiting for the appropriate resources to run, and we're kind of being super efficient with our time. So that's about it for now. And I'm kind of happy to stick around and help folks if they have any questions and stuff. So thank you guys. And we'll